Okay, so ladies and gentlemen, just to talk specifically about this evening's presentation, we're honoured to have Dr. John Ging. John is the incoming chair of the IET Ireland network. John is going to talk about Harmonics and specifically the challenge it presents to the Irish power system. There are a couple of rules for tonight. Tonight's presentation will not talk about any specific projects, and there's some sensitivities about that, so some of you who may have some particular project questions which are with regard to Harmonics, just to let you know at the start, I'm not going to ask him to answer specifics because that can have particular commercial implications. And I'm just going to basically hand you over to Dr. John Ging. So please.
So just a quick overview of what I'm going to talk about. My presentation is complete without talking about Eirgrid and what we do. Just kind of an idea of where the system's going in the next 10 years or so. A little bit about the theory of harmonics, so the codes, policies, all that good stuff. And then a little bit about how you can avoid harmonics, which is what most people probably are interested in, what I know least about, so it'll be an exciting part. And then some system experience, just what we've seen in the system in the past, what we're seeing on it in the present. But I won't be talking about any individual projects or nodes that anybody can work out who's connected there or anything like that. So that's kind of where I'm going to go, and then at the end there'll be a bit of a Q&A session, and hopefully I'll be able to answer some of your questions. So I suppose kicking off, most people probably know who Eirgrid is at this stage. There's ourselves and Sony in the north who operate as a transmission system operator, so that's the 110 kV network and above. We also have Eirgrid Interconnector Limited. Probably everybody here has heard of Eirgrid at this stage and how it connects us to GB. And then there is also Eirgrid Telecoms Limited, which not that many people know about, but it's there. And it's to package some of the fibre that's been put in with Eirgrid and hopefully sell some bundles to the UK at some point in the future. And we also operate the electricity market, so SEMO is kind of under Eirgrid's umbrella organisation as well. Just to give you an idea of the power system, this kind of gives some perspective for later on in the talk, I suppose. Just kind of identifying weak network areas and things like that. We've got a nice bit of network in the country, 4,000 kilometres of 110 kV, almost 2,000 of 220 and 500 odd of 400 kV. So that's roughly money point to Dublin, or just outside Dublin. 220 makes some nice figure of eights around the country, connecting the major cities. And then the bit in between is all 110, which is all the towns and everything else. And you kind of draw particular attention to Mayo and Kerry, which has got kind of small amounts of network, but as I'll show later, there's a lot of wind due to wind there. And then Northern Ireland, which is either 275 or 110 kV, and there's a nice bit of lines up there as well. So there's a nice circle around Loch Ney, and that's pretty much the network. And just in terms of interconnection, I suppose DC interconnection or HVDC interconnection does normally have some harmonics attributed with it. So we already have two interconnectors, Moyle and East-West. They're working away grand. We're looking at possibly going to France in the future. There's some feasibility studies being done. So where it's going to land is still debatable, so it's dotted line there. And then we currently have a tie line to the north from Louth to Tandragee, and the north-south is in process at the moment. So I suppose just to give you an idea of the amount of electrical converters that have come onto the system, an awful lot of the wind farms are basically just DC to AC converters. So I suppose Gate 1 was scattered kind of mostly in the northwest and southwest. It's about 0.4 gigawatt, and that was in 2002. 2005 saw 1.3 gigawatts. Some of it, or nearly all of it, is built at this stage. And it's kind of scattered again in the southwest and northwest, but some coming across the Midlands as well. And then Gate 3, which is currently underway, which is 4 gigawatts, which is really going to take us to 2020 and have our 40% energy from renewables from electricity. So that's kind of where we're going to go. You can see that there's an awful lot of wind farms due to connect in the west, particularly in the Cork-Kerry region, the Mayo region and the Donegal region, which are the weakest parts of the network, as we saw on the slide a couple of slides back. It's all the 110 kV network in that area. So that's just to give you some perspective of where the weaker parts of the network are and where we're likely to see some issues for harmonics. Then just how we're going to go forward from now till 2025, as it says, a good 25. We're going to build some new lines, about 1,150 kilometres of them, and also upgrade some of the existing ones just to take more of this wind towards the major hubs. So these are kind of the main corridors. There's about 300 projects in total, but the top 5 have been shown here. All of those are going to be overhead line, with the exception of obviously Shannon Kerry, which may need a submarine crossing, which will be cabled. So that kind of gives you an idea of where things are going in terms of the network. So that brings us on to the fundamental question of tonight. What is harmonics? The dictionary definition is an overtone accompanying a fundamental tone at a fixed interval. So it's kind of, if you've got a note being played on a guitar or something, there's going to be any other tones that are played alongside it. So it's also put down as artificial. So if you just strum a guitar, say the top string, you'll get an E, and there'll also be a load of other stuff coming out. But all that other stuff is always present there. So that's pretty much, they're called artificial, but they are there. And it's the characteristic that gives, it depends on their system. Like, you know, if you've got an E on a guitar and an E on a violin, why aren't they the same? Obviously they've got, you know, different materials make up the guitar or the violin, different lengths of the lines, that sort of thing. So it's kind of, it's dependent on your system itself, what your harmonics are going to sound like and the tone that you're going to get out of it. Allegedly it's pleasing to the ear, depends on who's playing your guitar. And it's not for power systems, I suppose. You definitely don't like harmonics on the power system. So, what are power system harmonics, I suppose, is the bigger question. Everybody knows what a 50 Hz signal should look like. It's 3 phases, R, S and T. So it looks something like that. Going into your home, you've probably got 1 phase. Going into a factory, you've got probably all 3. What harmonics tend to do is that they make it not so pretty. They destroy the nice sinusoidal waveform and give you horrible stuff superimposed on top. There's spaces scattered around if you want to do that. So, I suppose, how do we analyse power system harmonics? Obviously, we know what the phases should look like, the nice sinusoid shape, but we kind of have loads and loads of them superimposed on top of each other. So we have to go back to the further series. I apologise, there are some equations in this, but I'm not going to talk through them. Okay, so we've got our 50 Hz fundamental, nice, just single phase there. And then suppose we were to have, I don't know, the first 5 harmonics on the system. So you've got 50 Hz, which is the fundamental. Then you've got the first harmonic, which is 100 Hz, or it's called H2, the second harmonic. The third one is 150 Hz, fourth one is 200 Hz, fifth one is 250 Hz. So they're all there as well. What happens is they all get superimposed on top of each other and you end up with that waveform. So now, when you've got, you know, your Intel is being fed by a sinusoid, they're being fed by that instead, they're not going to be too happy. So our job is to try and eradicate that and get it back to the nice sinusoid. So I suppose the best thing to do is just talk about further analysis. What it does is it takes something that's in time domain, which is that square waveform, and splits it back into frequency domain. So it takes it and puts it back into the building blocks that we just talked about, and then spreads it out across the spectrum. So each of the frequencies all the way along, you can work out the amplitudes of them, and then just convert it using a simple integral. And you'll end up with something in the frequency domain, which the beauty of it is, means that you can now look at each harmonic separately. So you can study the first harmonic, the fifth harmonic, whatever one, independently of, instead of having to look at that horrible, horrible signal all on its own. So that's kind of what further analysis is about. I'm not going to go into all the equations and everything, it's just to give you an idea of how it works. So what causes the harmonics in the system? In essence, it's caused by non-linearity. Non-linearity of customer loads for the most part. So basically you've got a device, say you've got a voltage source that's sinusoidal shown there, and you've got some sort of device that's non-linear in its behaviour. So it could be a CFL bulb in your house or whatever it happens to be. And it draws load in a non-linear way, which the current will interact with that and give you a distorted waveform. So you see that the top current waveform is not the same as the sinusoidal voltage waveform. So that's basically what causes, you know, a harmonic current to be on the system. And this occurs at various frequencies up and along. The problem is that these harmonic currents then interact with the system impedance, and that gives you a harmonic voltage distortion at various frequencies. So that's the fundamentals of it. And then I suppose a lot of people, when they're talking about harmonics, will reference the total harmonic distortion. This is just a measure kind of how bad things are. It gives you a kind of a feel for how much heating could happen because of harmonics, or how much your waveform is away from the original sinusoidal waveform. So it can be referenced in either current or voltage. So I've got the zetas in there. It's basically the sum of all of the harmonics, or all of the voltages at each frequency squared, or currents at each frequency squared over the fundamental. So you can just sub either I or V in for zeta and everything's fine. So just to give you a feel, they're all going to have some sort of harmonic distortion. Even a perfect sinusoid, it'll never be quite perfect. So a typical linear waveform will be about 1.2%, whereas when you've got something like a rectifier here, the harmonic distortion is up around 80%, which is not great. I did say there were some equations. Unfortunately, these are the first of them, but everybody kind of understands this one. It's basically you've got three phases. They're all out of phase, or three phases, and they're all 120 degrees shifted from each other. What happens with different harmonic orders, so as you go up along the spectrum from 50 up to 100, 150, 200, all the way up along, they tend to have effects on each other. So I suppose I have an equation here, but I think it's easier to just show what happens. So we've got the third, the fifth, and the seventh just as random ones. Well, I suppose we'll talk about the third one first. On the third harmonic, if you soak the numbers into the equation just there, what happens is you'll work out that there's a rotation on the R phase of 0 degrees, a rotation on the S phase of 0 degrees, and on the T phase of 0 degrees. So ultimately, there's no rotation at all. So it's called zero sequence. On the fifth harmonic, you can plug the same numbers in, and this time around, on the R phase, it's 5 by 0 degrees, so obviously it's going to stay 0. But the S phase is 120 degrees out of phase, so multiply 5 by 120, you get 600. Which is the equivalent of being minus 120 degrees. And on the T phase, it's normally 240 degrees out of phase. You multiply that by 5, you get 1200, which is minus 240. You can kind of break things down. So what happens is you've got a negative phase, or a negative sequence on your phase, on the phases for the fifth harmonic. And then the seventh, it works out that it's a positive. So what in essence happens here is you're introducing some sort of torsion onto the system. And if that interacts with, say, a motor or a generator or something like that, it can cause your generator to have to do extra work to overcome this torsion that's happening. Obviously, fifth is particularly bad to have because it means you've got to do extra work to overcome on your generator or your motor. Whereas the seventh is more like the fundamental, it's spinning in the positive direction, so it's actually helping a little bit. It's still got currents there, so it's going to heat up your generator or your motor or whatever it happens to be. This is all for a balanced system, I suppose. If it's unbalanced, you have to use matrix methods. So if you have a different phase or a different amplitude, phase angle or amplitude on any of the phases, then you've got to worry about matrices. So I won't go into that too much, but I suppose everybody kind of wants to know what's the harmonic sources. And I'm going to start in reverse order, so starting on this side. Saturated ferromagnets. That was the traditional cause of harmonics in the system. Back in the day, when they were rolling out the high voltage grid, transformers were kind of the first and foremost. They introduced some harmonics onto the system. Basically, they would be operated slightly above their knee point, where they're most efficient, and you'd end up with the eddy currents in your transformers, which you call the heating effect, and you'd have some harmonics through that. Motors and generators are also kind of smaller, but they do contribute to harmonics in the same manner as transformers would do. I suppose in Ireland we don't have too many arc devices on the system. We did in the past. We used to have Irish steel there, but arc furnaces are particularly bad for harmonics. They spew out harmonics across the spectrum. Welding machines, fluorescent lighting, anything with an electronic ballast, any of that sort of stuff, they're all kind of under the arc devices. But the big one today, and the one that it's kind of brought the problem back to the fore, is power electronics. There's not too many devices around these days that don't have some sort of power converter in them, whether it be rectifiers or some sort of power supply or UPS or battery charger, inverters, all that sort of stuff. So as that is starting to come onto the system, so all your laptops, your TVs, your wind turbines, whatever it happens to be, they come onto the system and they introduce new harmonic currents at various frequencies. Then if that interacts with the system impedance, you can have harmonic voltage distortion. So just to give you a feel for kind of harmonics in question. I suppose the power electronics are fairly straightforward. It's down to the number of pulses. So if you've got K pulses, normally a converter would be 6 pulse or 12 pulse or 18 pulse. That gives you K times N plus or minus 1. So you end up with the 5th and the 7th, the 11th and the 13th, the 17th and the 19th in the case of a 6 pulse converter. For a 12 pulse, you have very, very small amounts of 5th and 7th. It'd be diminished by over 90%. But you'll still have the 11th and 13th, and multiples of 12, so you'll have the 23rd and 25th and all the way up along. And the 18th, then you'll have 17 and 19, but you still have small amounts of 5th and 7th and 11th and 13th as well. ARC devices are, as I said, they're all over the shop. Even and odd harmonics come up here. 2nd and 3rd, 4th, 5th, 7th, 11th, you name it, it's probably there. And even worse, they have some below the fundamental 50 Hz frequency, which is, I suppose, the subharmonic domain is what some people call it. And that tends to give out things like voltage fluctuations which lead to flicker. So you can end up having your light going on and off a lot of times in your room, and people find it pretty annoying. And then transformers, motors and generators. I have an asterisk beside the second for transformers, purely because it kind of only happens when they are energizing, and after a second or two that clears. But it does exist for a few seconds, and if you've got sensitive load, there can be a problem. 3rd, 4th, 5th, 6th, and 7th, it's basically the lower frequencies to do with transformers, motors, and generators. The 6th is actually an artificial harmonic that comes about because the 5th and the 7th actually give a torsion on the system, and it ends up inducing the 6th harmonic on a shaft or a bearing. So that's kind of the harmonic sources going forward. Why are they becoming a concern? Obviously, as I said just a minute ago, the increasing use of power electronics and converters are injecting more of these currents onto the system. And because the nature of the system is changing, it's interacting with this network impedance. A lot of cables have come onto the system, and they change the network impedance by bringing resonance points down the frequency scale. And what ends up happening is you can have a possible amplification of any harmonic currents that are present. So a lot of people kind of seem to think that cables are what causes the harmonics. They aren't. They're just things that can start to amplify. So if you put a cable into a weak part of the network, it could be okay. But if you put a cable into a weak part of the network and there's harmonic currents there, it can cause all sorts of problems. So what does it mean? I suppose it doesn't mean anything unless you've got a problem and there's something interacting with something else. Otherwise you can sit away with it for years. But when it is there, I suppose the first thing is you've got more currents in the system, and everybody knows currents on the system well, excess currents in the system can lead to higher losses, the I2R losses, so that's not good. You end up with overheating in your transformers, your motors, maybe neutral wires if you have neutral wires for your transformers. You might need to reconsider your specifications for them. Worse again, it can resonate with the system capacitor banks. There's a lot of cat banks around the system in various locations for voltage support. Any kind of resonance with them can cause your cat banks to fail, which isn't particularly good. Another thing I mentioned a few minutes ago is you can have shaft torsion brought on, and shaft currents if you don't have any bearings insulated properly, which can cause vibrations and basically break your motor or your generator. Telecoms interference has been kind of much flouted in the past. And then misfiring or incorrect triggering at zero crossings. I suppose the easiest way to talk about that is by demonstration. There's 50 Hz signal. Some power converters use the zero crossing, so where it goes from positive to negative, as a firing point for whatever they're doing in your converter. So every time it goes from zero, from high to low, you have a pulse. And what ends up happening is if you've got a harmonic like that happening at the same time as your pulse, you might not necessarily get the same crossing points. So in this case, you actually miss the designated point and have 2 more or 4 more crossings nearby, which is equivalent to about 750 Hz or thereabouts. So instead of having a 50 Hz signal, you've got what your converter thinks is a 750 Hz signal, which isn't particularly good for any electronics. And then just a scare picture, a picture of what happens to the capacitor when it gets a bit hot and goes. So that's kind of the bad things about harmonics. I suppose I did mention resonance a few minutes ago. I should probably talk a little bit about resonances before I go any further. So The big one is parallel resonances. That's excited by a harmonic current source. So if you've got any currents on your system and they interact with the impedance, and the impedance becomes quite large, you can have significant voltage distortion. So what happens is typically your system, well, I suppose, I'll show you the circuit first. You've got, as the name suggests, a parallel resonance. You've got an inductor and a capacitor in parallel. And it's excited by a current source, and it gives rise to an admittance YC is equal to J omega C, and Y for the inductor is 1 over J omega L. So just to plot that, the admittance of the inductor decreases with frequency. The admittance of the capacitor increases with frequency, and when the two of them collide, well, I've got conductance there as well. When the two of them collide, the admittance becomes, basically of the equivalent circuit, becomes quite low. But everybody knows that the admittance is the inverse of the impedance. And when the admittance is low, the impedance is high. And it becomes quite close to infinity. The only thing that's limiting it is that G at the bottom there. So the resistance basically is limiting how high the impedance gets in the system. So if you have a current that interacts and falls at Fn, which is the frequency of the harmonic resonance there, what will happen is you'll have a significant distortion in the system, which is not good. The other one is series resonance. So we've already talked about parallel resonance. So series, I suppose, as the name suggests, you've got a circuit in series. This one is excited by a voltage rather than a current, and the equations are based on the impedance this time, the reactance. Okay, so talking standards, there are three kind of main standards. There's actually a lot more of them out there, but the one that a lot of people referred to back in the olden days was the US standard, the IEEE, which is 519. I suppose 1992, I think, is the most recent version of it, but it has been around a lot longer than that. The UK standard, which is G5-4, it had G5-3 long before that, and I imagine it was a 2 and a 1 way back in the day. And the Irish, well, it's the IEC standard, but we have adopted that in Ireland as the planning standard. So it's IEC TR 61000-3-6, and it's from 2008. But all three of them are currently undergoing review in the hope of kind of refining little bits and pieces. And I suppose they'll become more harmonised as things go forward. I suppose just to talk about each of them, they all kind of try to do the same thing, and that is impose a limit at the point of common coupling, where whatever user connects onto the grid. The US one tries to do it in a very harmonised way, in that it supplies current and voltage distortion limits that's agreed between the user and the system operator. The UK one puts the onus on the user and basically says that the first comes, first served. The IEC one tries to do something similar to the US one, whereas it puts the onus on the user and specifies a voltage distortion limit. It kind of prorates it out amongst a cluster or a group of users if there are more than one user at a facility. So it tries to be a little bit more fair than just first come, first serve in the UK. So I suppose just to talk about the grid code is the rules we rock and roll by. We've got a clause in there on power quality. Power quality is more than harmonics, it also has flicker and some other good stuff in there as well. But it basically puts the onus on the users to ensure that their connection doesn't exceed the level of distortion allocated to them by the TSO, which in this case is Eirgrid. And there's something similar in the distribution code. And then it states that these limits are based on 61000-3-6, which we've already just talked about. So just to give you an idea of harmonic limits, I always like trying analogies that are kind of very simple. The last time I presented to UAT, I gave an analogy of throwing beat onto a train going to a beat factory. So this time I tried to go something much simpler. And I went for the kitchen sink. So the kitchen sink is just to show roughly the limits that you're allowed in terms of harmonics on the system. So the first one is the compatibility level. So that's the highest verified safe level. It's basically, you've taken loads and loads of measurements over years and you know that there's no problem when you're at this level or below it. Once you go beyond it, you're starting to get on shaky ground, so you kind of want to stay below that at all times. The planning level is kind of what every engineer thinks of having, at least be below the planning level. Try and maintain some sort of safety margin. So in this case, we've got a little hole there where the water can flow over if it gets too high. So The planning level is basically where 61,000-3.6 comes into play. Eirgrid uses that and allocates to the planning level with a margin maintained. And then the maximum emission level, that's really kind of the last chance saloon. You don't want to go beyond that. You want to retain that margin at all times before you hit the planning level, because things start to get hairy at that point. So that's the three kind of levels everybody talks about. And supposing you've got a leak onto the system. So in this case, it's your background distortion. There's always stuff on the system that's harmonic related, from transformers or from small-scale users, and, in your own home, your laptop charger or whatever it happens to be. It generates stuff and puts it up there. And in small amounts, it can get to whatever level. So that's the background distortion. It's going to take up so much of it. And then you've got whatever is between that yellow line and that purple line to fill with any site that comes in. And you don't really want to fill it if you can help it. But the next one in then is, supposing you've got a wind farm at site B. He's allowed to have a certain amount. And then another wind farm at site A is also allowed to have another amount. Depending on the size of the wind farm, they'll be allowed different amounts. But it has to remain below the maximum emission level. Then, supposing it starts to fill up. Provided everything stays below max emission level, everything's A-OK. But there may be some times where it gets close to it. And in that case, you're going to need some sort of a filter on site to make sure that your own turbines or whatever it is gets soaked up like a sponge and doesn't bother the rest of the network. If it does get to a situation where things are starting to overflow from the local site, so you're going beyond your node, you're going to the next node on the system, you're going to need to worry about other users on the system. So in this case, we've got two adjacent users. The toothbrush is immunity level 1, which is, I don't know, some device that's connected onto the system. Could be your TV, could be your computer, could be anything. And then there's immunity level 2 for some other device. And there's lots and lots of different devices, and they all have their own standards, and they all have their own immunity levels. But you really don't want to be messing with those levels. So in such a case that you're going to have an overflow from your node onto the system at large, you're going to need a filter. And in this case, you need a bucket. So that's basically what we've been trying to do in the last while, looking at various filters to try and minimise the impact on your toothbrush or your razor or whatever else it happens to be on the system. So, what most customers do? That's kind of the burning question for a lot of people these days. Some of you here are probably consultants for our customers or have your own wind farm or are interested in harmonics. So, what do you have to do in order to be compliant with the grid code and get your connection onto the system? The first thing you need to do is, if you're going to have cable on your connection method, come and talk to Eirgrid or the ESP or whoever it is that's dealing with your connection method. If there's a risk that you might have a cable or even a possible off chance, just mention it in passing so that we have an idea of what's coming, because these things do take time to sort out. And then also tell us about any other reactive power devices that you might have on your site. So normally we have a requirement that all pre-energization data, whether it be for harmonics or dynamics or whatever else, is submitted in advance of registration or energization, at least 1 year. In this case, for harmonics, you're better off to come as soon as possible because they can have long lead times, some of the solutions. So I suppose just to kind of identify the problem in the first place, we've got power quality meters scattered across the system, and it records at whatever station for a week-long period, a 10-minute time frame, what the harmonics are, and then we work out the 95% out of that, and make sure it's below the IEC standard. So we've got a recording, the kind of typical values there, and then we've got the IEC limits, which are beside it. So they're all below it. If they start to get above it, then you've got problems. So then you also have to remember that things change throughout the year. Obviously the system impedance changes, the loads change, depending on whether it's night or day or winter or summer or whatever. And you can just get an idea there of the seasonal variation. Well, it's not a great plot, but there's two bars beside each other. The taller one on that side is August, so that's kind of more summertime, and the lesser one beside it is November, so it's more wintertime. And you can see that it's dominated by the August summertime one. So the summer night valley load is when you have your worst case harmonics on the system. So we typically would study the summer night valley and maybe have a look at winter peak with summer night valley is the main one to look at. Then we start doing the modelling. So we have a model of the entire system. We use Dixon Power Factory. It models every single node, every single circuit breaker, every single generator. Not all the loads in the greatest of detail, like we don't go down to 220 volts or whatever, 230 volts. We would only kind of model down as far as 38 kV and DSO connected nodes. So you've got your Dixon Power Factory model. Obviously, we've got the background recordings from the previous slide. We lashed that into the model, and then we would look to make sure that we can recreate that. So the model should spit out what's been recorded in reality. Once we've got the two of them lined up, we can then add in new infrastructure, whether it be new cable, or whether it be new capacitors, or new turbines, or whatever it happens to be, the internal network of your wind farm. We can put in lumped or distributed models, geometric shapes of the cables, all of that sort of stuff can be all put in. So you've got a very, very accurate model. And then we try to assess the impact of these changes. So once you've added in this new stuff, what happens to the harmonics? What happens to the impedance? And then obviously you have to look at how things evolve. So you have to look at N-1 outages. So if you've got a maintenance outage or a tripped outage for whatever fault, is your wind farm or your data center or whatever it happens to be still compliant? And then we look at future reinforcements. So we know that there's a new line coming into the area in 10 years' time. What will that do for your harmonics? And then, obviously, if there's a couple of wind farms all beside each other connecting into the same node, we have to look at subgroups. There's no point in looking at them one at a time. They need to be assessed together and try and get a feel for how they're all going to interact with each other. And then different loading scenarios. So that's the summer, night valley, winter peak, different levels of wind and all that sort of thing has to be looked at. So what comes out of the model then is basically a series of plots, impedance plots. And we're able to work out from that the limits that will be allocated to each customer. So I've shown 3 customers here. One is a DSO, so it's kind of the big purple one down the middle. So they'll have lots and lots of customers behind that. They could have 10 or 15 other smaller wind farms all behind it. But DSP networks will allocate down to whoever is connected at their voltages based on the distribution code and whatever they work out from the equations. And then there's whatever applicants are at 110 kV. So applicant A and applicant B will be given it on a prorated basis, similar to what I was showing in the kitchen sink earlier. And you'll also get these impedance loci. So that's basically it. Each of those blue dots, I hope everybody can see them, corresponds to a scenario. So it might be intact case, it might be N-1, it might be winter night, or winter peak, or summer night valley, or whatever it happens to be, or future expansion. And then you draw these squares all the way around it. So it's kind of there's a set criteria for how to draw the squares. You can pick the furthest most to the right and draw a straight line straight down. The top one and the bottom one you draw a horizontal line and straight across. And then you kind of start off at the origin and just start spanning out until you hit one, and whatever the angle is there, you'll use that as your first angle up and angle down. So it kind of, as long then as you can remain within these squares, you'll be compliant with the grid code, providing that your harmonic injections, your current injections don't get larger than what's allowed. So that's the plan anyway, to stick to below those limits and within those impedance loci. So you give that then to your filter designer and they'll be able to use it to design a filter if you need to. Or you could just pick wind turbines that will be compliant. So back to what most customers do. This is the before, so after. So after obtaining these limits and loci, you then have to either purchase and install turbines that will be limited to those, so that you don't go beyond it. So your turbines might be able to do it on board. Otherwise, you'll have to install something like a filter to try and stay below those levels. And once you have decided what you're going to do, come back and talk to the system operator, because these things can interact with neighbours and it's worthwhile just checking that everything is okay. So if 2 people in a subgroup decide to get the same turbines, you could end up with new issues or whatever. So it's worth coming back and discussing. So harmonic mitigation options. We've already talked a little bit about resonances. Basically, if you've got a resonance, one of them that's a part of the cause of the problem. If you've got injected currents onto the system, that's another bad thing in terms of problems. So if you've got resonance and currents coming together, that's probably a worst case scenario. So that's scenario C there, where you've got a combination of new distortion and disamplification from the change in resonance. So the possible mitigation options include change the system strength, obviously increase it. Transformers themselves can act as a block for various harmonics. Passive and active filters, basically don't install on a cable in the first place, can change things and help you out. But that's not always possible, I suppose. And then limitation on the injections from your plant, so we've already talked about that a little bit. Or use of an alternative converter, so say going from 6 volts up to 12 volts or something like that. So the first one of those, the increase in system strength, is purely a system operator kind of step. There's not much you can do about it in your wind farm. The next ones, I suppose, are all either system operator or customer. Anybody can change or decide on transformers or different filters, and limit an amount of cable. That's up to you, but it could, come back to Eirgrid or the ESB networks and say, no, we can't accommodate that. It's just not going to be feasible. And then the last one is customer only. Like only you can pick your turbines, and only you can make sure that they're compliant. So I suppose just talking about system strength, I do have another equation here. This one's fairly straightforward. It's the root of the short circuit MVA over the megalarge capacitor bank. So that will give you a rough idea of where your first harmonic resonance is going to occur. So normally the network is fairly inductive. We've got fairly long 110 kV or 220 or 400 kV overhead lines, which tend to have kind of resonances higher up the scale. But when you connect capacitive elements, so something like an underground cable or new capacitor bank or whatever it is, that will lower that resonance frequency. So it'll basically, you want to shift it back up the scale. The higher up the scale it is, the better. It's further away from any kind of device's resonances. And then obviously there's a danger in that, because in order to increase your system strength sufficiently, in some cases in very weak areas, you might need to significantly increase your short circuit currents. So I suppose here's an example where you're in a weak area of the network and you put in a new cable, and it's brought the harmonic resonance down as far as the 6th harmonic. So you can see you've the inductive part, the capacitive part, they've brought it down to the 6th. And you can see the short circuit strength in that area, the Ka value, is in or around 4 Ka where that resonance occurs. So supposing we were to increase the system strength in that area, I should say this is for the connection of a 20 kilometre 110 kV cable. So we increase the system strength in that area by maybe adding a new transformer or meshing the node further, bringing new lines to it or whatever. We need to increase it by like 14 Ka just to shift it back up to the 12, 13, 14 harmonic range, which is a significant increase in short circuit currents. So basically, how do you do that? I suppose I already mentioned you can bring new transmission circuits, install higher voltage transformers, or else connect stiff generation to the area, so CCGT or something like that might need to come in order to increase it up. Then I suppose the other thing is, safety is the big concern on the grid, and you need to make sure that your switchgear is rated to handle these higher short circuit currents. So I suppose you want it to be high enough that it's able to increase the harmonics out of the range but you want to keep it as low as possible, because you want your switchgear to work when it needs to, so your circuit breaker will open whenever there's a fault. The other one I mentioned was transformer winding connections. Basically, transformers are typically they have the capacity, if they're Y delta transformers, that you can catch some of the tripling harmonics, or the 3rd, 6th, 9th, or whatever, in the actual windings of the transformers themselves. And also, transformers are very, very good in terms of they're a big tank that absorb harmonics, particularly at higher frequencies. So the higher frequency harmonics tend to not be able to pass through transformers. So I suppose there's an idea for the triplins. They can just circulate forever in your delta windings, but you need to be able to make sure that it doesn't overheat or whatever. And then the other thing to remember is that tripling harmonics can flow on a neutral conductor, so you need to be making sure that neutral cable is fairly highly spec'd, or you could have overheating, and that's not good for a transformer. The other thing then is shunt capacitive filters, or shunt passive filters. The idea of that is to shunt your harmonic current into the ground or away from the network in general. So the idea is that it absorbs at some point across the spectrum. You have to design based on an RLC design, and obviously take the network impedance into account, and then it's able to take care of whatever harmonics you want eradicated. So obviously you want to make sure that it works under all operating conditions. I already mentioned that the impedance changes throughout the year from summer night valley all the way through to winter peak. So if you've got a passive filter that works great in summer night valley, it mightn't necessarily work at winter peak. So that's something to bear in mind when you're designing passive filters. As I said, it's RLC, and it's tuned to either a single harmonic or lots of harmonics, depending on how you want to do it, or you can have multiple banks of these filters all together. And you have to remember one thing. Filters are made of RLC. The capacitive part of that filter can change your voltages at 50 Hertz. So you need to make sure that you tune your filter accordingly. Otherwise you can have unwanted voltage control, and that your voltage will be increased above 110 kV and possibly significantly so. This is just kind of an idea of all the different types of filters out there. These are the single tuned, double tuned and triple tuned. It's basically just putting additional circuits in parallel, and you can see that the single tuned brings a nice low resonance, so you've got the series resonance. At whatever point you had your parallel, you'll be able to cancel them out and you'll end up with not many problems there. The double tuned has got two resonances, and it tends to kind of work if you needed to do two fairly close by harmonics. Not so great for very spread out ones. You might be better off just building two single tuned close by. And then triple tuned then is a more elaborate form. It's worth noting that the single tuned does increase your losses at the 50 Hertz frequency. Double tuned not so much, and it is quite usable. Whereas the triple tuned also suffers from high losses at 50 Hertz and is more elaborate than the double tuned. So tend not to see too many triple tuned filters out there. And then damped passive filters. Basically these are similar to the previous lot, except there's a resistance brought into it, and the resistance tends to spread out the effect of the filter. So you won't get the same peak, like you won't be able to take out an individual harmonic in the same manner. It won't remove the fifth on its own just as well, but it will take the fourth and the sixth beside it a little bit as well. So it can be useful if you've got 3 or 4 harmonics all together. You can reduce them all a little bit, but you won't ever probably eradicate them completely. And again, these have got various types. There's second order, third order, and C type. And a lot of them that tend to be designed today tend to be C type filters. So I suppose then there's active filters. These are quite different to the passive filters. Basically what they do is they measure the harmonic currents that are present on the system, and they work out exactly what's needed to basically cancel them out. So if you've got harmonic current at a certain phase, they'll put in one that's the exact opposite phase and it'll cancel itself out. The problem is that they're very expensive to implement, and there's not that many of them around. I don't know of any that's on any transmission network yet, but I'm sure they're coming down the line. And the other thing is that if you've got one very close to another one, it can actually interact with the neighbouring equipment, so you could end up with a beating effect, and they could end up actually making things worse. So you have to be very careful when designing active filters. Then other schemes, I suppose, I've already mentioned, limit the harmonic injections from the equipment, or install on-site filters. The other one is connect by overhead line. That's not always possible. Generally, when you're coming looking for cable, you've already had the overhead line ruled out, whether it be by planning or whatever other issues. So it might not always be feasible to go with that one. And the last one is to select an alternative converter, so a different number of pulses or materials or whatever it would be. Then measuring harmonics. On the Irish system we use inductive VTs, so basically it's impossible to measure harmonics at the 110 kV or 220 kV or 400 kV level. You have to step them down to a more manageable voltage. And we use VTs to do that, and they're just inductors in the label. But you have to remember that all inductors, or all of these VTs will attenuate some of the harmonics, so you're not getting an exact replication of what's going on there. So just to give you a feel, that this is a study that was done in Dresden University, I think. The green plot shows the 66 kV VT, and you can see that it's quite flat all the way out past 2 kHz and close enough to 3 kHz. So that kind of covers all the way up to beyond the 50th harmonic. The blue one, on the other hand, is the 110 kV, and it's okay up as far as I suppose where things start to change here is just around 1.5 or thereabouts. So it generally beyond that point, you're not quite as sure about your reliability of your VT, and you can't say the harmonic are perfectly recorded. And then for 220 kV, the red plot, obviously that shoots off very low down, so it's very, very hard to make any kind of harmonic measurements at 220 kV and beyond. So kind of at 110 kV, we're happy enough with them up as far as a 30th harmonic. From 30 to 50, which is where the standard ends, I suppose measurements are a little bit more difficult to come by, and you need kind of higher grade equipment to be able to work that out. And then beyond 110, it's very difficult to do so due to the larger impedances. Then just I suppose we have these power quality disturbance recorders. They just hook into a cabinet that's connected to that CT or VT, and they do a 10 Hz sampling rate. They're able to work out the currents or voltages that are involved. And you need them for performance monitoring to make sure that nobody's above their limits, and also for us to be able to model it correctly and make sure that our model is verified. We get reports every month that tells us what's going on there, all the way up to the 50th harmonic, some interharmonics. So in between the second and third, there's lots and lots of non-integer values that you can have harmonics at, and the THD, and obviously 10-minute averages. And then if there's an event that happens on the system where you've got a spike above 2%, which is kind of when you're starting to get into danger territory, or any kind of other strange behaviour, you get an immediate report from these power quality recorders. Then I suppose we're on to what's actually on the system. The first, I suppose, is our own. The east-west interconnector is the first plant to be issued harmonic limits in Ireland in recent times. Basically, it's got filters at AC and DC level. On the AC side, it's got harmonic filters at the 5th, the 8th, the 32nd, and the 60th. And it also has some filtering on the DC side. And then at Shotton, which is in Wales, it also has the 60th and 32nd, but it has the 23rd harmonic. There's some harmonic problems around that voltage level there as well. And then on the DC side of things, it's got 9 harmonic filters, and it's moving faster as well to make sure that you've got no, I don't know what that A is, but there should be no A there. So. But you've got 9 harmonics blocking any filter or any harmonics on the DC connection. So I suppose there's lots of different devices in eWIC that makes it work. The voltage source converter itself is actually quite good at blocking harmonics. You set a high enough number of switching angles, we've got 11 in this case, it's able to eliminate about 10 harmonics. So a lot of the spectrum from 0 all the way up to 30 is eliminated by the converter itself, which made sure that we didn't need too many filters involved. Then we've also got side filters, which is the 30th, 2nd and the 60th, which I'd already talked about. These are to shunt the higher order harmonics down to earth. And we also have the transformer delta windings as well, which is able to take care of those triplet harmonics. So it takes them all, well, substantially evades them as well. And obviously there's the 5.8 on the Irish side and the 23rd on the UK side. So just to give you an idea of what these things look like, I suppose a lot of you might have made it out as far as Portadown to see eWIC at some point in the past. If you haven't, it's a nice station out in Meath beside Woodland, 400 kV station. It looks something like the top diagram, but there's probably a better picture here. At the bottom will be on your right. Actually, that picture there shows the 3 transformers going into the hall, into the valve hall. And then the picture on the right side is the 5.8 44 megabar filter that's outside in the AC. So that's kind of the outside of the eWIC. And then inside we've got the filter bank for the 32nd and the 60th. So they're an 80 megabar filter and a 25 megabar filter. And they're to block the higher order harmonics and shunt them to ground. Irish Steel, some of you might remember Irish Steel, some of you might not, was a big arc furnace it was active from 1937 to 2001 or thereabouts, but it had a high voltage connection from 1962 to 2001, 2002 kind of time frame. And that was basically connected at Hall Boland station in Cork. We had 2 110 kV circuits. Earlier on in the 60s, when it connected first, you can see that Cork was quite weak in terms of number of lines into it. But that obviously changed as time went on. And by the time that the 80s came around, and there was a 50 megawatt arc furnace and also a 12 megawatt ladle on top of that at Irish Steel, we had significant build in the region, and there was a connection to Raffine on one side of the river, one side of the bay, and Whitegate on the other side of the bay. The plot on the right shows basically what Irish Steel did to the load in Ireland. The red line that's shown is the week after Irish Steel was decommissioned, and the blue line shows the effect of that 50 megawatt arc furnace on the 12 megawatt ladle on the system when it was constantly turning on and off, and that it would cause the load to jump up or down at a given time, which is fairly hard to manage, and frequency obviously would jump along with it. In terms of harmonics, it was basically shunting out an awful lot of lower order harmonics. There was also problems with flicker, where you would have the lights in Cork would flash on and off continually in around 8.8 hertz or thereabouts, so you'd have your lights on and off 8 times a second, which is pretty annoying. So there'd be constant monitoring of the flicker and the harmonics in the NCC itself. And if the flicker went above a certain value in the flicker meter, they'd be on the phone to Irish Steel to try and get them to sort it So this is basically an SLD of Irish Steel and how they were connected. And you can see that there's two SVCs connected into Irish Steel, and they were connected in an always-on configuration. If either of the SVCs were turned off, the harmonics became above the limits, the IC limits, and Irish Steel had to go offline. So we had second and third order harmonics and a high-pass filter as well. So that's kind of just to give you an idea of what they were trying to filter out down there. And in the system today, I suppose, a lot of people are interested in what's going on. We're in good shape. Everything is okay and below the limits at the moment. There are some areas where things are starting to go awry a little bit. I suppose that happens in N-1 outage conditions, that we're starting to see us getting closer and closer to those levels. We're not quite there yet, but we're getting there. And it's not a good position to be in, so I suppose that's why tonight's talk is going ahead to try and educate people. This is a very recent measurement at a station X. I wasn't told what station, because you can basically work out who's connected there and what equipment they have or whatever else. So it's at station X. It's somewhere in the southwest, so Cork, Kerry, Clare, Limerick, somewhere around that region. And you can see the total harmonic distortion, which is the black line capping everything off. And that's basically that the square root of the sum squared over the fundamental. So we had the equation earlier on. So you can see the green line is just underneath the black line is the dominant harmonic. That's the seventh. And that's not a particularly good harmonic to have, because it can affect your generators and your motors and things like that. And we know that it's caused by electronic converters based on the equations earlier on. So basically we're being dominated by the 7th. So this happened recently. It's just the 20th of September through to the 16th of October. So it's almost live data. And you can see that it's pretty much constantly the 7th harmonic that's up there. And then the 5th, the yellow one, is just below that. So it's the next highest up. So again, power converter frequencies. And then just kind of the bar chart representation to kind of give you an idea of what's going on. The THD, as you can see, never gets below 0.3%. There's always something there. And for the most part, we're in good shape. So the 95th percentile, remember, is where the IEC specifies to. And we stay below 1 on the THD. And the THD for IEC is 3, is what you're allowed to. So, even if like we were to go to the 95th to the 100th percentile, the most we get to is about 1.5. So we're about halfway there. But the problem area is the 7th harmonic. If you look at that, you see that there's the 50 to 95% who are around the 1 mark. That's fine, but you've got to remember that at the 7th, we're only allowed to go to 2. So we're halfway there already at this station for the 95th percentile, and then for the 95 to 100. So say you're in an outage or something is going on, you could end up in that situation, and very quickly you find yourself up around the 1.4, 1.5 mark, which is getting closer and closer to that limit. So that's kind of where we are today. System is okay, but we have to keep an eye on it, I suppose is what the message is. And then I suppose just to say what we're doing, we have extensive work in progress. Obviously we're trying to identify and mitigate any of these issues before they happen. We're talking to everybody, like that's what tonight's about, or a lot of our other meetings would be just educating people on what harmonics are and what they can do to your own equipment as well as to the grid. And then develop a policy around charging, so somebody's going to have to pay for any filters that are required, and that's kind of difficult because you've got to go to somebody and say, look, previously there wasn't problems, there could be a problem in the future, and now we need to pay for it. And then obviously just testing the harmonic injections and the background distortion, you just have to keep monitoring it all the time. And we're just reviewing that grid code clause, because you can see that it covers it, but there are other things that can come under it, and because this area is evolving all the time, we need to make sure that the grid code is up to date, and that we can effectively police the system with it. And then internationally, I suppose the same sort of thing is going on. Other system operators are trying to test for all these harmonic injections in their systems and try and monitor them and make sure that they're not there, and just mitigate against them as well by putting in filters or putting in, increasing the system strength or whatever it happens to be. And then at an advisory level, I suppose, is where all the good stuff is happening. Everybody's looking at the standards again, going back. It's been a while. The most recent was the IEC, was the 2008 one. G5-5 in the UK is kind of under a lot of scrutiny at the moment. It's almost ready to go. And then obviously beyond 50 hertz. Tonight I'm only talking about up as far as 50 hertz, but there's a lot of stuff just beyond that, and we need to go from 2 to 150 hertz. Beyond 2 kilohertz is what it is. We need to go from beyond 2 all the way up. Power line carriers, that's kind of how we transfer data on the power lines themselves. They operate just beyond 2 kilohertz. Electric vehicle chargers tend to have resonances on, or just above the 2 kilohertz mark as well. And again, smart grids, which is how the grid is going to communicate in the future, and how everybody's going to be an Internet of Things, I suppose. that also is in that kind of ballpark range. So we need to kind of effectively work out what can be ejected by harmonic currents in those areas, and make sure it doesn't interfere with electric vehicles, smart grids, or our own communications. So that just brings me on to the last slide. It basically points to a website page which has an information note, or there'll be a couple of notes there very soon, on harmonics. So if you missed anything tonight, or if you want further clarification, just reference that and you'll be okay. That's me done. I'll take any questions now.
Okay.